Okay, today's lecture is about the asymptotic equipartition property. So this is one of the most fundamental mathematical objects or mathematical ideas in information theory. The basic idea here is that you pick a sequence at random from all of the possible sequences. Its probability will be very likely to be very close to a certain value. In other words, there's a certain sort of average probability that most sequences will have. So this lets us sort sequences into two groups. One is called the typical set, in other words, the set of sequences that all have roughly the same probability, and the other set is the atypical set. So it'll turn out that the typical set has almost all of the probability, and the non-typical set has essentially none. So for the purposes of, for example, data compression and source coding, what you can do is you can disregard the atypical set and only encode sequences in the typical set. We will also show that entropy gives us an idea of the size of the typical set, and that's why entropy is so important. So the basis of the asymptotic equipartition property is the weak law of large numbers. This is a statistical law, or a statistical theorem, which we will not prove, but is very intuitive. So let's let x be a random variable. And let xi, or I equals 1 to n, represent outcomes of x, of the random variable x. So we can define sample mean is given by, if I have n outcomes of x, in other words, you can think of x as the roll of a fair die, and xi, the outcomes of that, for instance, if you roll the die n times and write down the number showing on the face of the die, that would be xi. The sample mean is given by, for n outcomes, we'll call it x bar n, which is equal to the sum of all the outcomes, xi, 1 over n. So 1 over n times the sum of the outcome. So this is the naive way of calculating an average. You just take all the outcomes, add them together, and divide by the number. On the other hand, expected value is given by expected value of x, which is equal to the sum over all possible outcomes of x, of the probability of that outcome times x. So we've seen that, we saw that last class. If you like, this can be thought of as the experimental mean, and this can be thought of as the theoretical mean. So the weak law of large numbers says in the limit as n goes to infinity, the probability of the magnitude of the sample mean minus the expected value. So in other words, the error, the magnitude of the error between the sample mean and the expected value less than epsilon. So this statement is, what's the probability that the expected value deviates from the sample mean by more than epsilon, or by less than epsilon? In the limit, as n goes to infinity, that's 1. For any epsilon greater than 0. So what does this mean? Basically, this means if you pick any sufficiently large n, then, or excuse me, if you pick any epsilon greater than 0, then there's some sufficiently large n so that the probability of the sample mean deviating from the expected value is approximately equal to 1. So in other words, what this says is that the sample mean and the expected value should be about the same in the long run. And this is highly intuitive. So this is why, if you don't even know what the probabilities are, you can still take the sample mean, because we would expect this to converge to that. Put another way, let's say that x is a random variable where if I have a fair die and I roll that die, then let's let x equals 0 if the roll of the die is not equal to 1, and x equals 1 if the roll of the die is equal to 1. So what would we expect? What would the expected value be? X is 0 unless the roll of the die is 1. If the roll of the die is 1, then x is 1, and the probability of that is 1/6. So therefore, the expected value would be 1/6. If we did that with the sample mean, basically what you'd be doing is you'd expect that 1/6 of the time a 1 comes up. So therefore, if you take the sum of all of those outcomes, you would expect it to be approximately 1/6. So this is intuitive. It's what we're familiar with. It's what people crudely call the law of averages. You sort of expect things to be close. You expect things over time to be close to average. There's another way of saying this that we're going to use. So another way of saying in the limit as n goes to infinity, this is true. Another way of interpreting this, for sufficiently large n, there exists epsilon and delta. Excuse me, for sufficiently large n and any epsilon and delta greater than 0, then the probability that the magnitude of xn minus the expected value of x is less than epsilon is equal to 1 minus delta. So in other words, I can choose any epsilon and delta that are larger than 0. That's implied by the definition of the limit. So in other words, I can pick epsilon and delta as small as I like, and there must be an n that's sufficiently large, because ultimately, in the limit as n goes to infinity, this must be true. This statement must be true for any epsilon and delta greater than 0 if n is sufficiently large. So in other words, if I wait long enough, I can get arbitrarily close to the mean with arbitrarily high probability. So we're actually going to use this form more than this form. Okay, so how does this apply to sequences?